thank you everyone to joining for this 70 seminar series. So today it's a great pleasure to welcome Franck Mauconduit from the CEA NeuroSpin. So Franck did a PhD in Grenoble, so in the Institute of Neuroscience. We did the PhD at the same place, so we had already the occasion to meet and to share the same lab. And then he moved to Paris as a Siemens clinical scientist. And now he's in NeuroSpin as a system manager of the Iseult system, so the 11.7 Tesla. And today he will show us the latest result of in NeuroSpin at 7 Tesla and 11.7 Tesla. So thank you, Frank, to accept the invitation, and please tell us everything about ultra high field and extreme high field MRI.
Thank you very much, Frédéric. So I'm really happy today to talk to you about the work that we have done recently about the 11.7 Tesla, but as well all the work that we have done prior to that at 7 Tesla. So today I represent the work of the methodological team. So I would say it's a presentation on behalf of the whole Iseult group and the MR methodological group. So CEA is Atomic Energy Commission in France. It's one of the institutions of research with others that you may also know, CNRS and INSERM, the other research institution in France. But CEA was dedicated to atomic energy at the beginning, and now today it is engaged in military research, in renewable energy research, as well as advanced factories, health as well, and still about the civil energy and nuclear plant dismantling. Of course, I'm part of the health research, and in this section, so NeuroSpin is one of the research platform. It's a neuroimaging platform that search for human brain singularity in the healthy condition and as well as in the pathological condition. And there are multiple interdisciplinary groups in physics, electronics, medicine, mathematics, statistics, image processing, and also psychology and sociology. So all these groups are gathered at NeuroSpin through different institutions, but is hosted in CEA within the NeuroSpin building. So the idea is really to probe the human brain and search for the singularity of the human brain, and using an exceptional platform. And for the clinical platform, so we have a 3 Tesla MRI that was installed at the beginning of NeuroSpin in 2008. It's a Prisma Fit today. We have a 7 Tesla that was installed a few years later in 2010, which is still a Magnetum 7 Tesla, so it's a very old kind of 7 Tesla system of Siemens. And we now have today the 11.7 Tesla, and I will talk about this today in the presentation. So just important things are going to occur, because next year we are going to replace the 3 Tesla with a CMAX. The 7 Tesla is going to be replaced as well for a TeraX. And today I will talk about many works that we have done at 7 Tesla for the years, and also the work that we have achieved really recently at 11.7 Tesla. And the work at 7 Tesla was, in the MR methodological group at least, was really to prepare things for the 11 Tesla research. So why ultra-high field is interesting? So the benefits, of course, are about the SNR, and it has been shown already quite in different papers, and this one is one of them in Poman paper, that the SNR increase more than linearly with the field strength. So this is very interesting and can be exploited for improving resolution, for instance, or for exploring other nuclei as well, and going to the sodium imaging, for instance. The CNR is also positively affected, and this makes the 7 Tesla a very interesting tool for fMRI, for instance. It is also interesting to notice that the noise correlation is good because it will help us to increase, for instance, the acceleration in the images using GWAPA techniques, for instance. And in principle, also, we could benefit with the broadening of the rays in NMR. But these different benefits are also challenged by different aspects. The B1 plus inhomogeneities, of course. The SAR as well would increase. The B0 inhomogeneities also increase linearly with the field. And the motion, since we are going to try to get higher resolution, would also be a problem in this case. So all these aspects have to be managed to really get the power that the ultra-high field can give us. So I will present you several of the studies that we have done at 7 Tesla, just to show some examples of these benefits. So for instance, we have studied the hippocampus and showed that in Alzheimer's disease, volumetric study can help to see the alteration, for instance, that is specific in the subiculum. So it's not a shrinkage of the whole hippocampus, but some subparts of the hippocampus are affected. As I said, fMRI is also, of course, a great interest for ultra-high field at 7 Tesla, and our connectician at NeuroSpin use it quite a lot. And here is an example of a study looking at different aspects of the numerical processing in the brain and showing that the intraparietal cortex is really play a central role in this. We also done some studies about the X nuclei. For instance, mapping the lithium in the brain. So as you may know, the lithium is not naturally present in the brain, but patients with some psychiatric disorder get some lithium as a medication, and mapping the lithium in this case was really interesting to see how the lithium go into the brain for different subjects. It's variability in terms of spreading around the brain, and we could also correlate the lithium concentration with the lithium in the plasma, for instance. And one other study was about sodium concentration, where we could show that we have an increase of tissue sodium concentration, and that could be used as a biomarker for Alzheimer's disease. So these are some of the examples in terms of application, but our group has worked a lot on solving the problem for the B1 plus inhomogeneities. And I wanted to show you a bit what the work that has been done in regards to this issue. So as you may know, when we increase the field, the Larmor frequency is increasing and the wavelength is decreasing and gets approximately to the size of the brain or even smaller at 7 Tesla. And this so as a consequence that we see shadowing in the images or we see contrast lost in some other sequences. This would depend on the sequence. And also this was really for us something very important because the problem that we see at 7 Tesla on the head, so we can see this problem already at 3 Tesla on the abdomen, for instance. But of course, going to even higher field strengths, we knew that it would be even a higher problem that we had to deal with. So for this, one of the solutions that have given quite some promise is parallel transmission. And it needs specific hardware. You need to have a full RF chain, additional RF chain, as well as a coil that can handle this additional RF chain. And using this technology with a standard pulse is called the circularly polarized mode, where we send the same waveform on each channel with the same amplitude and the adequate phase. And in this case, we don't solve anything. We just get the standard behavior of excitation pattern that we get also with one transmit channel only. But if we modulate the amplitude and the phase on each of the channels, then what happens is that the hotspot, the high flip angle location and the low flip angle location would shift in the tissue, but would not be really managed for getting flip angle homogeneity. So to go for something that is even better, we need to acquire the B1 plus field maps within the tissue. For this, we can use specific sequences like the saturated turbo flash sequence or the actual flip angle imaging or even the dream imaging. Those have been different sequences used by different groups. And with this, you can get the B1 plus fields within the brain for each of the channel in the chain. You might also need additionally a B0 map because this would also have consequences on the excitation pattern. And if with this information, you do some optimization on the RF using the block equation, you can eventually get some kind of pulses. Here is an example of the so-called Katy point pulses that can help to actually homogenize the flip angle excitation. So this example is one of the pulses that can be used. And the Katy point pulses has been published by our group in 2012. And I will explain a little bit how these kind of pulses can actually improve the homogeneity of the flip angle. So let's consider two voxels that are separated in space. So these two voxels eventually see a different B1 plus field. The voxel 1 will see a higher B1 plus than the voxel 2. And if we apply a pulse, RF, then we'll get a different tilting in these different voxels. So this is the first subpulse, for instance, in the Katy point. Then we can eventually apply a gradient, and this gradient would also affect both voxels, but in different way because they are separated in space. So let's consider eventually that the voxel 1 doesn't see anything because it's at isocenter, and the voxel 2 gets shifted in the transverse plane. And finally, if we apply a second sub-RF pulse this time with a different phase direction of the B1 plus in plane, in the transverse plane, then we can actually flip the aimantation in the voxel 2, but without touching the voxel 1. So in the end, we can see that we get the homogeneity that we look for with a 90-degree pulse, for instance. So this is a really simple case, but you have to just have in mind that this is what the optimization tries to do, actually. It tries to find a way that all voxels get excited by the same flip angle, even though at the beginning, each of the voxels see a different B1 and are also located in different locations and would be affected differently by a gradient. So for several years, we have been working a lot with this kind of technologies to apply these different pulses for inversion, for refocusing pulses, for cut points, for the excitation in 2D, in 3D, in slab selective. And this has given rise to a certain amount of publication. So I talked already about this one, about Klaus in 2012, about the cut points. Then later on, Aurélien Massir has done a PhD on trying to do excitation and refocusing pulses for the space sequence. Then another PhD student worked on the TOF angiography at 7 Tesla, trying to make some tone pulses, this kind of pulses with a ramp in excitation throughout the brain. But still in this case using parallel transmission and trying to get this homogeneously throughout the brain. We even tried to do some development at 3 Tesla with Raphaël Tomitrico that done work on doing the RF, dynamic RF shimmy in the abdomen to specifically try to homogenize in certain pathological condition, specifically when you have ascites, then you have some water around the belly, and then the inhomogeneity in the abdomen is very high. And we have shown that we can improve this situation using, for instance, a prisma with two channels, two transmit channels. And finally, also another work about, so this work was about T1 and T2 measurement using PTX. And finally, a work also using other kind of pulses that are not cut points, that are great pulses, but great pulses, I will talk about it just in a few minutes. So with all of that, you need a lot of algorithm and being able to handle the block equation quite quickly for the optimization. You need the maps, you need to do some masking, some B0 mapping, you need a coil, you need a SAR management, and eventually also you need some GPUs to do this calculation quite quickly. And you can eventually end up with some pulses to be played on the scanner. But with this whole process being a bit complicated, you can also expect delays and issues. And this is why we have been thinking about a solution where we could simplify a bit the way to do a parallel transmit examination. So what I've described is that once you do the localizer, you need to do a B1 plus mapping, a B0 mapping, and then do the pulse design to be able to use the parallel transmission at the console. So we were thinking about a way to actually externalize this pulse design framework to prepare this in advance so that when you put the patient on the table, it's much more easy eventually to acquire the images with PTX pulses. And this is the concept of the universal pulses that was published by Gras in 2018. So the idea is to actually take a database of B1 plus and B0 maps that are acquired prior the subject of interest, and to do some pulse design that would fit for all of these different brains. And you get a pulse that you can finally try to apply on a different subject that is not present in this database. It's actually indeed that it's kind of working quite well. Think that should be pointed out that if you do this, you have really the time to get the database with taking the time to have really high quality B0 and B1 maps on healthy subjects. You can do the offline pulse design, and eventually, if these are really intensive, that's not really a problem because you have all the time you need to do that. You can also check for the performance and check for the SAR and redo the design if required. And in the end, you get a plug and play solution where when you have a subject on the scanner, you don't need any B1 plus maps and you don't do tailoring pulse design. So you're already ready to actually do the PTX examination. So this work was first done at NeuroSpin using a homemade coil. But of course, it would have a better interest if we try this on the Nova coil. So we got in touch with some of our collaborators, and specifically first with DZNE in Bonn, where we went to acquire the database on the Nova coil because they had this coil at the time, and we tried to set these universal pulses on subjects on the Magnetum 7 Tesla scanners at the time, so it was in VB17. Then, having these pulses, we got in touch with other collaborators in Minnesota and also in Maastricht to actually try also these pulses on other scanners with that have the same coils. And it turned out that it was working well as well. And then more recently, in 2000, just after the COVID, in 2021, we began to implement also this solution on Terra system. And we got in touch with the first Terra system installed in France that was in the CHU de Poitiers to actually try to implement the sequences and try the pulses on this scanner as well. So this is the kind of images that we got. We did that on the MP2H, MP2H. We also implemented the T2 space sequence. We added the inversion with a T2 prepared, which is specific to get the nice gray white matter in the flare sequence. So it's a T2 prep flare sequence. And quite easily when you do that, then you can also add the double inversion recovery sequence that is available at lower field, for instance, on the 3 Tesla scanners in Siemens environment. And since we had all this ready, tested on other sites, we actually shared this package of sequences via the C2P platform of Siemens. And also Aurélien Massier, that was largely involved in this development, did this article in the Magnetum Flash of Siemens. So now we are really happy because we have shared the package quite a lot with many collaborators throughout the ultra-high field community. And we hope that this can be helpful. But as I said, this work has been done first on classical 7 Tesla in VB17, then on the Terra in V12, and we hope that we can include also Terra X system in the near future. But as I said, we are going to upgrade our 7 Tesla, so this is definitely something that we are going to do quite quickly now. So, of course, all of this is interesting if we apply this methodology to patients for clinical studies, for instance. And in NeuroSpin, we have tried these sequences on multiple sclerosis at 7 Tesla, on our 7 Tesla. So using the Nova coil, because in between the time we had the opportunity also to buy the Nova coil. And you have here some examples of images with some multiple sclerosis lesions that appears in the deer space, for instance, or even in the MP2H sequence. Of course, in this case, for multiple sclerosis patients, it's also interesting to actually acquire T2 star weighted images. And we did this kind of acquisition as well using PTX pulses. In this specific image, you can see the central vein in the multiple sclerosis lesion that the radiologist would like to try to see very well. We have done also some comparison between 3 Tesla and 7 Tesla and show that we, of course, can improve the lesion depiction with 7 Tesla. So yeah, as I show in this slide, we can still have some artifacts. And this is where the additional kind of pulses I was talking about, the grape pulses, come in the game. This specific artifact that we see is definitely because of the B0 inhomogeneities close to the brain air barrier, and using some other kind of pulses where we actually let the algorithm the freedom to change the RF and the gradient at any point during the pulse, we can get improved results. If additionally we enforce some specific optimization to take care of the B0 inhomogeneities. So this kind of pulses have a very high number of degree of freedom compared to KT points, and this is what helps to actually get better solution. But it's getting very intensive in terms of computation, and in some pulses, for instance, if you take an inversion pulse, where you need several milliseconds to actually perform the pulse to get the inversion flip angle. And considering that every time point is a 10 microsecond width or length, it's a big number of degrees of freedom that must be optimized. So it really helps in this case to take the time to do this computation and use the universal pulse concept. And in terms of results, it was really interesting. And you can see in these images, on the top was the KT point optimization compared to the grape optimization. And the performance is much better in the region with high B0 inhomogeneities. So we were really happy with this kind of pulses. And in addition, it also helped to reduce a bit the length of the pulse that is good for the imaging parameters. So other examples of a recent usage of the PASTEUR package in other groups, I have two of them. One is very recent because it has been presented at this ISMRM by the Cambridge group, led by Christopher Roger. They did a cohort of, they are going to do a cohort of up to 35 patients with epileptogenic lesions. And in this study, they did already about 20 patients, and they compared the 7 Tesla PTX sequences and the CP mode using partly some of the PASTEUR package for specifically the anatomical sequences. They also did some diffusion imaging, but this was their own PTX development. And yeah, not going too much into the detail here, it's just to show that, yeah, we can see that now there is some interest to use this kind of technology. And also a group of, in China, because we have also shared with many of the 7 Tesla Terra system in China. They have done some acquisition on brain metastasis, showing, of course, in the cerebellum, specifically, an improvement in the contrast. And this was also specific because this was, as far as we know, the first time that there was some contrast injection with the MP-RAGE using the PTX sequences of the package. So I've been talking a lot about the 3D sequences, and in the 3D sequences, there is also some interest to go for slab selective pulses. And when you want to have a slab selective pulse, you transform a rectangular pulse into a sync-shaped pulse, for instance, adding some gradients. And if you think about the KT point, it's actually quite straightforward to replace the rectangular pulses with sync-shaped pulses and additional gradients for slab selectivity, for instance, or even actually slice selectivity. And these kind of pulses are called the spoke pulses and helps to do slab or slice selective PTX excitation or even eventually inversion. And we have been working on the space sequence to have a slab selective space sequence recently. And in this case, there is some additional difficulties because the excitation is selective, and we need to add a non-selective refocusing pulse, and then you have the variable flip angle non-selective pulses. This is the way it is done in the product sequence. And for each of these pulses, we have replaced them with PTX pulses. And this is a recent work done in collaboration, again, with our close partner in DZNE. This is Daniel Lowen, a PhD student that has worked to do this integration and this kind of pulse calculation. And we have shown some nice results. And here comparing the slab selective space between CP and universal pulse acquisition. And what is really nice with the slab selective is that you can have the axial orientation, and then you can have a very nice in-plane resolution. So you are getting closer to what you could do, for instance, in 2D. And this is the kind of development that we try to release in the next PASTEUR package. So we can also apply this kind of slab selective pulses to even simpler sequence like the 3D GRE and making the 3D GRE slab selective. And again, what is nice here is that you can use this because this is the kind of protocol that is really standard for SWI measurement. Still using these 3D slab selective pulses or even non-selective, we have worked on the fMRI protocols using a 3D EPI, again, from Rüdiger Steinberg in DZNE, and we integrated the pulses to do this in PTX. And for us, this is an important step specifically because, so first we showed that we get the same kind of fMRI functional results using the 3D EPI than a 2D SMS. And this is, in our sense, the way to go for 11.7 Tesla, because we think that it's going to be very difficult to have the PTX simultaneous multi-slice EPI in 2D. And it's much more straightforward to go for the 3D PTX EPI. And what about the 2D? In 2D, you might eventually have to deal with independent pulses that are specifically designed for each slice. And in this case, it's possible already to get nice results, but we have done some work to even go with a better technology, and we would like to also have some calibration-free universal pulse in 2D. And we have done this other kind of optimization where we don't calculate specific pulses for specific slices, but we calculate some kind of functions that are optimized in terms of PTX to be able to analytically calculate the spoke pulses when we know where the slice will be positioned during the examination. So this is a way really to try to have a calibration-free universal pulse in 2D. And we have done this work and presented this work in 2022, where we show that once the meta pulse is computed, then it's a simple analytical PTX solution that helps to get an homogeneous exhalation, whether we change the slice location and eventually even the angulation. So this kind of work we would like to also integrate in other kind of 2D sequences. I want to briefly mention other aspects. We have been also working on acquiring faster. So why acquiring faster? Because when you have a 7 Tesla, you have an extra SNR. And having an extra SNR, eventually you want to acquire higher resolution. But even though you have the extra SNR, going to higher resolution, then makes you spend more time to do the acquisition. So it's very important to also think of ways to get this very high resolution in some more efficiently in some way. So recently we presented this work about the MP2 RAGE. So in MP2 RAGE, we like to get this uni image because it's very nice in terms of receive profile homogeneity. And in the literature, there have been different ways of getting different kind of contrast. And we wanted to find a way to merge all of this and get a possibility to have either the uni image or the different flows or the flows mean that has been proposed by different groups. And we end up with this idea of a time-efficient MP-RAGE, where we reduce the acquisition length by reducing as much as possible the inversion times in the MP-RAGE, as well as the repetition. So in some way, we acquire as fast as possible this MP2H, but then we use the EPG formalism to choose the flip angles of the trains, of the first and the second train. And finally, at the end of the process, we don't get the standard uni image. So we get modified, acquired uni image, and we still can eventually compute the T1 map. But then we use this information to go back to the synthetic uni image by this relationship that is in the MPUH framework. And eventually we can also reconstruct other kind of synthetic acquisition, reconstruction like the flows mean or any other kind of contrast. And this work has been applied and showed that compared to the standard uni acquisition, for instance, we could save up to 19% of acquisition time. Then we didn't have some kind of issue setting the partial Fourier. We could have removed this partial Fourier acquisition and still gain the time, and also in the same time gain the true spatial resolution that helps to resolve the lesions, the small lesions eventually in the brain. And on the cohort of multiple sclerosis, as I talked a bit earlier, we also applied this kind of techniques and show that the time efficient was really helping a lot because of this additional resolution that we get, even though it's actually shorter to acquire. So this is, in our regards, really interesting. I want to just briefly mention, because I see that the time is floating, that we have been working also on non-Cartesian acquisition. And this is called the sparkling algorithm. We used a target sampling density, and going from an initialization, we try to find trajectories in K-space that are under the gradient constraints. And enforcing these gradient constraints, we really get trajectories that we call sparkling trajectories that have a target sampling density globally, but locally, we still get an homogeneous density of the sampling points under the gradient constraint for these specific trajectories. And this, of course, goes very well with the concept of compressed sensing. And we have been applying this kind of trajectories in 2D, in 3D, and we got some very interesting results. So just to mention, we did that on the 3D GRE T2 star, for instance, really getting some nice acceleration in the compressed sensing framework. We also applied this kind of technology on the X nuclei acquisition in sodium, for instance, in this case. And we think that it's also something that could be beneficial in fMRI because it's kind of a radial acquisition where we go at the center of K-space every spoke. So it could be very, very interesting, and we are trying to go in this way to actually have some kind of time-resolved fMRI acquisition. So now I think I need to spend some time left, or I hope so, for this work at 11.7 Tesla. So NeuroSpin has been built on this project actually. So this project began in 2001, and in 2000, in 2001, and in 2007, NeuroSpin was funded and opened to receive this magnet. It has some specific characteristics. So it's, of course, 11.7 Tesla. It's a wild bore to be able to do whole body imaging. And this was specifically chosen also to minimize the interaction between the gradient and the magnet. The homogeneity in terms spatially and the homogeneity in time is very similar to what we have in other kind of ultra-thin magnet. And one very specific aspect is that it is operated in driven mode. It means that we have an external power supplier that is always connected to the supraconductor. So it means, for instance, that if there is any issue that happens, we can get away the current without losing the supraconductivity or the helium. And this is operated at 1.8 Kelvin. So many time has been spent until the system arrives. I don't have time to go in all those 16 years in details, but this is what happens when the system arrives at NeuroSpin and was installed on the actual platform that has it still today. So, of course, in 2017, it was not yet ready to scan because, as you see, it's just a magnet on the platform, but it's not an MRI at all yet. But this is the reason why in the years after that, there was some time spent to do this installation. And we have done many tests to look for the gradient magnet interaction because it was a big question. Since, for instance, it's the reason why in the NIH, the 11.7 Tesla quenched and broke some years before we try on our system. So one of the discoveries when we did all these tests was that the third order shim is an issue for us at specific frequencies. And we decided to disconnect the third order shim of the B0 shim because we think that we have a more stable gradient operation without this third order shim. But this is also interesting to know with this for the 7 Tesla because at specific frequencies, it also is the case on the 7 Tesla magnet. And if you really want to have more information about that, Réseau Hubert on his layer fMRI website has done many tests, and you can have really details where you see that close to this high frequencies of the gradient, we get worsened images. So it's very important to look for the right bandwidth, and especially if you have the third order shim connected. So the imaging equipment of the system is really like a Terra system. It's in V12U, and we really operate the system as we would on a 70 Terra system. Apart that, we don't have the Nova coil, and we have been building our own coil to do our first study in vivo. This study has been called the PREM study. And the goal of this study has been to evaluate the field effect on the human at 11.7 Tesla, because as far as we know, it was the first time that we put some human at this field, and especially at this, for a whole examination of about 1 hour and a half. So we did 40 healthy volunteers, 20 were kind of scanned, but it was at 0 Tesla, so they didn't know about that. And we also acquired real images on 20 other volunteers at 11.7 Tesla. So we did a lot of different tests to check for the health. And for this study, we got the approval a bit more than 1 year ago in February 2023. And we did the study with the real images between July 2023 and the beginning of 2024. So all these images are on their way to be published. The paper is in review, but it's in good shape. And there is also a preprint already available about that. So the imaging protocol was kind of standard for ultra-high-field MRI examination. So localizer, B0, B1+, of course. We did a lot of PTX in this case. We acquired 3D multi-echo GRE in nominal RF shim mode, as well with dynamic PTX. And we did some other 2D and 3D acquisition, and I will show some of them. So we used, of course, all the technology that I have been talking about before. So this is the difference that we see between the nominal RF shim mode when we don't really do any kind of PTX and compared to the 7 KT point design specifically for this brain. So this was multi-echo GRE sequence. So with 4 echoes. We also acquired T2 space in 3D. In this case, it was an acquisition of 0.55 millimeter isotropic. So it's already quite interesting. Of course, we should definitely go even higher. So it was already quite a long scan time, but we'll try to even push further this kind of resolution. This was really the first test that we were able to do. So this image, not a lot of people have seen them because they are really recent. We didn't even show them at this ISMRM. They have been reconstructed by Simon Robinson using his clear SWE reconstruction algorithm on our 3D slab selective acquisition. So we think they are really, really wonderful. And so, of course, the SWE acquisition is the top contrast that we can have with this kind of ultra-high field. So it's already impressive with this first acquisition. And we did acquisition T2 star in 2D. And of course, for us, it was interesting to do a comparison between what we can get with very high resolution. And I really insist here, it's very high resolution, even for the 3 Tesla sequence image. And this is why we get this poor quality, because we did the exact same protocol with the exact same duration. And the higher signal to noise ratio and even the higher contrast is really expressed here, even already at 7 Tesla, but also at 11.7 Tesla, of course. So if we zoom in a bit 7 Tesla and 11.7 Tesla images, this is what we get. And we can see really, really a lot of veins. This is very impressive. So we really want to have the next study ready to go on with these acquisitions. And we also acquired this sagittal orientation in 2D, also with the T2 star GRE sequence that depicts a nice foliation in the cerebellum. So we have been communicating in scientific Congress, so at ISMRN this year, about this study. The paper is already in a preprint format available, but should be available soon. And also, you should know that eventually, if you want to have see further these images, they are available via Figshare. And we have been also communicating recently, actually before the Congress, in a general way, and this has been quite, at least in France, but we know that there was also some articles outside of France, and many already researchers saw this work through this communication. But of course, what's important, it's what's coming, because we are here for research. So now the PREM study is finished. There are really no issue with the subjects that have been scanned. So we just are going to prepare for the next studies. And of course, now it's a new scientific journey that begins, and we want to do cognitive neuroscience with our specialists in NeuroSpin. We are going also at some point to use these images in pathological condition. And we also have a full program of acquiring X-nuclei images. So I want to thank you for listening. I'm sorry I was a bit long, more than I expected, but this is the whole group of the methodological team. And I will be happy to discuss with you if you have any questions.